This is a video of problem set 13 where we start talking about periodic trends, which will become important to understand things like size of atoms and how easy it is to remove electrons from atoms and things like that. And there are certain trends that exist on the periodic table for these behaviors, and so we need to introduce those trends and use some rationale to explain them. So we're going to jump over here, have a little mini lecture on periodic trends before we go through and try and answer these questions. Okay, the most fundamental principle that needs to be understood when it comes to periodic trends, and really all of chemistry plays a role in it, and that is Coulomb's law. Coulomb's law defines the force of attraction between two charged particles. So, it is written as the force of attraction is proportional to the charge of thing 1, the charge of thing 2, divided by the distance between them squared. Okay, so this proportional sign means that if you wanted to actually do math with this, you would need a constant, but we will not be doing any math with Coulomb's law. We'll just need to use it for conceptual understanding. And as a result, we're happy just leaving it with conceptual. So again, you're never actually plugging numbers into this equation. You just use it to understand. So we can understand Coulomb's law in the context of like magnets. You have two charged magnets. One's positive and one's negative. They're attracted to each other, and there are two ways that we can increase the force of attraction. The first is by changing the charge on those magnets. If we increase the charge, what happens? Well, they're going to be more attracted. The second, if we leave the charge the same, we can change the distance between them. And you think of magnets, are magnets more attracted to each other close up or far apart? Magnets are more attracted when they're close together. So as radius, or the distance between them, decreases, that means the force of attraction is going to go up because that distance is on the bottom of the equation. So hopefully that makes sense, and now we're going to talk about this in the context of atoms. So on the periodic table, I'm just going to draw one quickly. Okay, so we've got this periodic table, and for atoms, let's kind of talk about what these variables could be for atoms. We could take this and say the force of attraction is going to be proportional to, and force of attraction between what? Well, in this case, we're talking about the force of attraction between the negative electrons in the atom and the positive nucleus of the atom. Okay, so the charge of one thing is just going to be the charge of an electron, so I'm just going to put E there. That's never going to change. But the charge of the other thing is going to be the charge of the nucleus, right? And we usually refer to the charge of the nucleus with the atomic number, which tells you how many protons are in the nucleus. More protons, greater charge. So those are the two charges we're dealing with. And then as for the distance between those two things, one thing that we could use to kind of represent that in the context of atoms could be like the n level. All right, we know that higher n levels are further away. And so I'm now going to take this adjusted Coulomb's law, and I'm going to use it as rationale for some of these periodic trends. So we know that as we go down the periodic table, our n level increases, right? What happens when we go across the periodic table? Does n level change? It doesn't. And so n, that distance, is what we're going to use to describe periodic trends when we're comparing things up and down. Across the periodic table, Z changes. Right, as I go across the periodic table, I'm adding more protons, and therefore Z is going to change. And this leads us into a discussion of an important concept, and that concept is Z effective. Z effective, instead of referring to just the number of protons that are in the nucleus, refers to the number of protons, or the charge of the protons, that the valence electron actually feels. How many protons are having an effect on that outside electron, or effectively, how many protons does it feel? So let's do a little exercise to talk about this. So let's say that I have hydrogen. Hydrogen has one one proton and one electron. So if I were to ask you, how many protons does this electron see or feel? It feels 1. So hydrogen has a Z effective equal to 1. Z effective equal to 1. Now if we were to go on to helium, helium has 2 protons. It's got 2 electrons. How many protons does this guy see? It can see 2. So helium's Z effective equals 2. But now, if we go down to lithium, lithium has 3 protons, 2 electrons on the inner N level, 1 electron outside of that. So, does this electron see all 3 of those protons? Okay, the answer we would say is no, because 2 of those protons essentially are being shielded by core electrons. And so that outside electron only really sees, it's only really affected by 1 electron. As we kept moving across the periodic table, what's next to lithium? Beryllium. Beryllium is 4 plus. Electron, 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 electron. How many does this guy see? Well, there's 4 there. 2 are being shielded, so that beryllium sees 2. And I could keep going with boron. If you did boron, you'd see Z effective is 3, carbon is 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. So what we see is Z, we don't really care about Z, right, because that's not the charge that the electron necessarily feels. What we care about is Z effective. And as we go across the periodic table to the right, just as we just showed, Z effective increases. But what happens when we go down the periodic table? You go from hydrogen down to lithium. Z effective didn't really change, right? So we're going to use Z effective to explain trends when we're comparing things to the right and to the left. Now, keep in mind, you're not going to be really calculating Z effective. It's not; these aren't actual real calculations. This is just kind of a very simplified model to explain it, but it works really well in the context of these periodic trends, and so that's why we use it. So what you need to understand is, as you go down an N level, as you go down the periodic table, N increases, and when N increases, the force of attraction decreases. As you go across the periodic table, Z effective increases, and when Z effective increases, the force of attraction increases. So with those 2 explanations, we can explain all the periodic trends. So that's your little mini lecture about Coulomb's law in the context of atoms, and let's take a shot at this problem set. So what is the difference between a group and a period on the periodic table? Group, I believe, is a column. Make sure I turn that around. Yep, groups is columns. And period then is a row. Okay, groups then contain similar reactivity elements, and periods contain elements with increasing numbers of protons. Therefore, they're adding electrons to the same, same shells and subshells. All right, the periodic table can be divided into roughly 4 blocks according to the type of subshell being filled. State the subshell being filled in each of these blocks. We talked about that in the electron configurations. We've got S, we've got P, we've got D, we've got F. There are also different families of elements on periodic tables: listed transition metal, an alkali metal, a halogen, a noble gas, an alkaline earth metal, a nonmetal, a lanthanide, and an actinide, and a metalloid in that order. Okay, so if I were to look at this periodic table, let's just kind of break down what's where. So transition metals is pretty much this D block. So anything in there is a transition metal. Alkali metal, so I guess I could give an answer. So transition metal, iron. But there's lots of answers you could give. Okay, alkali metal is this first column in the S block. This is alkali metal. So something in there, lithium is an alkali metal. Okay, halogen. Okay, halogen is, so this is noble gases. Okay, these are now the halogens. So halogen could be like fluorine. Okay, so we've got alkali metal, we've got halogen, a noble gas, so those are the noble gases, so iodine is a noble gas. Alkaline earth metal is these guys, the second column. So let's say calcium is one of those. Non-metal is, so we have this kind of line right here. That's rough, but everything on there, on this side is a non-metal. So like, I'm going to say carbon is a non-metal. Lanthanide, this is lanthanide. Lanthanides, these are actinides. So Ce is a lanthanide and Th is an actinide. And last thing, a metalloid are things along this zigzag. Silicon is along that zigzag. So again, there's lots of answers you could have given there, but you do need to understand what the different parts of the periodic table are called. All right. In which set of elements on the periodic table are the p orbitals being filled? All right, alkali metals we said are here. That's s orbitals. Halogens are here. That looks like p orbitals. Actinides and lanthanides are down there. And transition metals are characteristically in the D block. So just halogens. All right, we want the size, ionization energy, and electron affinity are all properties that show definite trends across the periodic table. Describe the trends for each of these properties going down the group and across a period. Okay, so let's talk about what each of these things mean. First, size. Size just is the distance between the electrons on the outer shell and the nucleus. So how do we think ionization how do we think size changes on the periodic table? Well, as I increase n levels, okay, that is going to be making my atom bigger. Okay, so that's simple enough. As I move across to the right on the periodic table, what's happening? My Z effective is increasing, which means my force of attraction is increasing. So that's going to pull the electrons in the atom closer to the nucleus because they're each feeling more proton pull, which means as we move across the periodic table, our elements actually get smaller. Okay, so size increases down to the left. All right, next is ionization energy. Ionization energy is the energy required to remove an electron from an atom. So let's talk about that. As I go down the periodic table, right, my n level increases, so my force of attraction decreases. So that as I move down the periodic table, my force of attraction decreases, which means the amount of attraction between the outside electrons and the nucleus goes down. When that happens, it becomes easier to remove an electron because the force of attraction is decreased. So ionization energy decreases going down, so that means it increases going up. It's harder to pull electrons off of atoms up here because they're so much closer that the force of attraction is higher. Now as I move across the periodic table to the right, the Z effective increases, which means the force of attraction increases, which means it becomes harder to remove electrons. So that means that ionization increases to the right, which means we could draw it up and to the right. And I think the last one asked about is electron affinity. Electron affinity is kind of the opposite of ionization energy. Electron affinity is saying how badly does an electron want to take, does an atom want to take an electron. So ionization energy is the energy to lose one. Electron affinity is how much it wants one. So what wants an electron more? Well, if I move down the periodic table, my n increases, so the force of attraction decreases, so these guys are less likely to pull an electron from the outside than these guys. So electron affinity, how much you want an electron, is going to increase going up. Z effective, as I move across the periodic table, increases. So my force of attraction increases. So element here is going to be pulling on outside electrons more than here. So electron affinity increases to the right. So similar to ionization energy, we increase up and to the right for electron affinity. So I can just take that. I'm just going to drop it right there. Make it a little bit prettier. Okay, explain the reason for the change in atomic radio across the periodic table as well as down a group. Identify each statement as true or false. Oh, that should be down there, but I just kind of explained how this happens. So you can just rewind and listen to it if you want. All right, let's identify these as true or false. Ionization energies are always negative. Question, if I'm trying to remove an electron, that's what ionization energy is. Okay, I'm taking an electron from an n level and I'm trying to rip it away. Okay, does that require energy or release energy? That always requires energy. And therefore, this should not say negative. If we want this to be true, there we go, should be positive. This is false. Oxygen has a larger first ionization energy than fluorine. Well, we know the trend for ionization energy increases up and to the right. So oxygen, so carbon, nitrogen, oxygen, fluorine. That's the order on, and then neon. That's the order on the periodic table in that second row. So oxygen has a larger first ionization energy than fluorine. That's not true. Fluorine is further to the right, which means it's going to have higher. So this is also false. Oxygen has a smaller first ionization energy than fluorine. And lastly, the second ionization energy of an atom is always larger than its first ionization energy, so that's true. Second ionization energy means after I've lost one electron, if I wanted to lose another one, that would be the second ionization energy. And that's always higher because once you remove an electron, removing another one is trying to rip off a negatively charged ion or electron from a positively charged atom. That becomes difficult. There's other reasons involved, but that's just an important concept to know. Okay. Moving on. When an atom forms an ion, its radius increases. When an atom forms a cation, its radius decreases. Explain why this is so. All right. So when an atom forms an anion, that means that it gains an electron and its radius increases. So let's think about that. Let's say I just had, I'm just going to draw a valence shell with 4 electrons. Okay, and it's got a certain number of positive charges in the middle. Okay, when I form an anion, I'm adding an electron, and I'm not adding any protons, which means each of these electrons is feeling the same pull as they felt before, but now there's another electron in here, and electrons repel each other. So as soon as I try and squeeze another electron in there, they repel each other, they're all going to push out a little bit, which is going to make my radius increase. Similarly, if I have an atom and I want to form a cation, that's removing an electron, which means now there's less electron repulsion in that outside shell, and all of them can squeeze a little bit closer to that nucleus. Hopefully that makes sense. All right, so we're now going to arrange the following atoms and ions in order from smallest to largest radius. I'm going to pause real quick and grab a periodic table. Okay, I've got a periodic table here, and so now we can do these. So we're trying to talk about smallest to largest. So remember, size increases down and to the left. So using that, we can look at the periodic table. So in this case, we have strontium, I'm going to get a better color. Let's do blue, strontium, krypton, bromine, rubidium, argon. So rubidium, argon, bromine. Okay. Down and to the left. So the furthest down and to the left is going to be the biggest. We want to rank from smallest to largest. So we want to start at the top right. So that's going to be argon, and then krypton, and then bromine, followed by strontium, and then rubidium. Alright, then we have neon, neon plus, and neon minus. So remember, when I add an electron, what happens? My radius increases. When I lose an electron, my radius decreases. So that means smallest is going to be neon plus, followed by neon, and then neon minus. Alright, this next one. Just going to look at the periodic table here. And I'm going to have, what do I got? Aluminum, cesium. Where's cesium? Neon, rubidium, rubidium, neon, sulfur. Just moving down and to the right. So smallest is going to be neon, followed by sulfur, aluminum, rubidium, cesium. Okay, now we have we've got chlorine, chlorine minus, cesium, cesium plus. Alright, so chlorine's obviously smaller than cesium, and chlorine minus is going to make it bigger because when I add an electron, the extra electron repulsion pushes out that outside shell. And then I've got cesium and cesium plus. Well, cesium plus is going to be smaller than cesium because you remove an electron and there's less electron repulsion. In this case, when you move that electron, you actually lose the entire 6s orbital, which is going to make you shrink a lot. So that's good. Cesium plus is smaller than cesium. Alright, and next we have K plus, so K's here, Ca2 plus, argon, Cl minus, and S2 minus. Interesting. So all of these, Ca2 plus, potassium plus, argon, Cl minus, and sulfur 2 minus, all of these are going to have the same number of electrons as each other. Okay, they all have the same electron configurations, and they all have electron configurations like argon. Cool. So does that mean they're all going to be the same size? No, because they have different numbers of protons. And more protons means smaller size, because those protons are pulling on those outside electrons stronger. So what has the most protons here? The most protons here is calcium. So even though they all have the same number of electrons, calcium has more protons, so calcium 2 plus is going to be the smallest, followed by K plus, argon, chlorine minus, and then sulfur 2 minus. Sorry, 2 minus, purely because of the difference in the number of electrons on those ions. All right, number 5. Compound NaCl consists of sodium cations and chlorine anions. Sodium and chlorine ions are not the same size as they are in their elemental state. Explain how their relative sizes change, larger or smaller, in relation to their size of their elemental state. Alright, so Na goes to Na plus, loses that electron, and when you lose an electron without changing anything else, you're going to get smaller because less electron repulsion in that outside shell. Cl goes to Cl minus, it gains an electron, which increases the electron repulsion in that outside shell, which is going to make it larger. Now it's important to remember this is the case because we're adding an electron without adding any protons. That's why it gets bigger. If we were adding an electron and a proton, the atom would actually get smaller. In the depiction of the crystal structure of salt to the right, which ions are the purple ions, which are the green? Well, so I've got sodium, which then gets smaller, and chlorine, which then gets bigger. Well, sodium is bigger than chlorine, but once it loses that N=3 shell, when it loses that one electron, it's going to be more like neon in its size, and that means that the smaller one is probably going to be sodium. So purple, I would say Na is purple, and sorry, Na plus and Cl minus is green. All right, which of the following atoms has the smallest first ionization energy? All right, so ionization energy. Wow, energy increases up and to the right. So again, I can just grab the periodic table here and compare the elements that it gives me. So we've got aluminum, phosphorus, strontium, gallium, rubidium. So which has the smallest? Smallest is going to be down to the left, so that's going to be rubidium. Awesome. All right, number 7. The first ionization energies of hydrogen and helium are 1,300 kilojoules per mole and 2,300 kilojoules per mole, respectively. Yet, the electron removed from both of these originated in a 1s orbital. Explain in 1 to 3 sentences the larger ionization energy observed between these two elements. All right, we know that ionization energy increases up and to the right. Okay, they just want us to explain hydrogen is 1s1. Helium is 1s2. Why does it take almost twice as much energy to remove an electron from helium than from hydrogen? Okay, well, helium and hydrogen are in the same row, and when we're comparing things in the same row, we're going to use the effective. So again, hydrogen +1 with 1 electron. Helium is +2 with 2 electrons. How many protons does this electron feel? It feels 1. How many does this electron feel? It feels 2. So the pull on this electron is almost twice as much as the pull here. So higher is the effective, means higher force of attraction, which means it's more difficult to remove an electron for helium. So that means higher ionization energy. Another particularly interesting exception to the trend in first ionization energy is found comparing nitrogen and oxygen. So let's just look. Ionization energy increases up and to the right. So if we're comparing nitrogen and oxygen, we would expect oxygen to have a higher first ionization energy, just based on the trend. But the first ionization energy for nitrogen is actually higher than oxygen. Offer an explanation. Often when you're asked to explain exceptions like this, it's a good idea to write out the box diagrams. 2s2, so that this was oxygen. No, let's do nitrogen first. 2s2, wow, 2p3, and then oxygen would be neon, 2s2, 2p4. So basically we're saying we would expect oxygen to have a higher ionization energy, but in reality it's harder to remove electrons from nitrogen. Why is that? Well, if you look at this, nitrogen's full here, half full here. Oxygen is full here, and 4/6 full here. Does nitrogen want to break that half full behavior? No, it would rather not. Whereas oxygen has some electron repulsion there. If you were to take away one of those electrons, it would actually bring it to a lower energy state, and as a result, it's easier to remove electrons, easier than you would expect to remove electrons from oxygen when compared to nitrogen. So again, often if you can draw it out like that, you can find out why the behavior might be the way that it is, and that's why we have an exception in ionization energy between nitrogen and oxygen. All right, getting there. An electron can be removed from sodium or rubidium by electromagnetic radiation, the photoelectric effect. Which element, sodium or rubidium, would require the shortest wavelength to remove the electron? Now, we've talked before, when we were talking about wavelength, shortest wavelength should automatically scream out in your head. Highest energy. And we're removing an electron, so what type of energy is that? Ionization. Highest ionization energy is really what this question is asking. Well, ionization energy increases up and to the right. So if I'm comparing sodium and rubidium, sodium's definitely going to have a higher ionization energy because it's further up on the periodic table. As a result, I would say that sodium would require shorter wavelength because it has a higher ionization energy. All right, based on their position of the periodic table, predict which atom will have most negative electron affinity. All right, this is a good opportunity to explain a little bit more about electron affinity. So electron affinity is how much an atom would like to gain an electron. Now remember, when we're talking about Bohr's model, if I had an electron way out here and it came down into an atom, that would be losing energy, that electron would, and so energy would be released as a photon. So all of these electron affinities are all going to be negative numbers because energy is being released. Pretty much all going to be negative numbers. Again, because energy is being released when an electron falls towards a nucleus. So things that have a higher electron affinity or a greater tendency to grab electrons, they're going to have a bigger negative number, is how we would say that. So based on the position, predict the atom. So really, when it says the most negative electron affinity, it's asking for the highest electron affinity, and electron affinity increases up and to the right. So compare chlorine and argon. Oh, this is a good opportunity as well. Electron affinity increases up and to the right, but not for the noble gases. Because how much does argon want to gain an electron? Well, if it gains an electron, it's going to have to open up a whole new energy level. That's not energetically beneficial. So the noble gases are actually exceptions to that up and to the right rule. So, excuse me, we got chlorine, we got argon. Chlorine is going to have a higher electron affinity because argon doesn't want to gain any electrons. All right, potassium and cobalt. Cobalt's further to the right. It's going to have a higher Z effective, therefore it's going to be pulling more on those outside electrons. All right, we got sulfur and germanium. Sulfur is further up and to the right, therefore it's going to have a higher ionization energy. And then we have tin. There's tin, SN. There we go. And SN and TE. Wow, why can't I find it? You're probably like looking at it right now, wondering why I can't find it. There we go. Wow, that was bad. All right, so tin and tellurium. Tellurium is further to the right, and therefore it is going to be higher in electron affinity. Okay, photogray lenses for eyeglasses darken in bright sunshine because the lenses contain tiny, transparent silver chloride crystals. Exposure to light removes these electrons from the Cl- ions, forming a chlorine atom in an excited state. Electrons are transferred to the Ag+ ions, forming silver metal. Silver metal is reflective, producing the photogray color. How might substitution of AgBr for AgCl for AgCl affect the light sensitivity of photogray lenses? In answering this question, consider whether more or less energy is needed to remove an electron from Br minus than from Cl minus. All right, so we've got this. So AgCl is really an Ag plus stuck to a Cl minus. So light comes in, it removes an electron from the Cl minus, that's what's showing here. Light comes in, takes the electron out of the Cl minus, gives it to the Ag plus, making silver metal. So it's really what we're asking here is, well, what if we did this with Br minus? What would happen? Well, what's easier to remove an electron from? Which is what's harder to remove an electron from? Br or Cl? Ionization energy increases up and to the right, so Cl is going to be harder to remove an electron from. Remember, because going up to lower n level, so the electrons are closer to the protons. Which means Br is easier to remove an electron from. I'm just going to write that real quick. Br minus is easier to remove an electron from. What result could that have if you use Br minus in your glasses? Maybe your glasses will turn reflective in not very bright light, right? So I'm going to say they become shaded too easily. You can imagine that would be annoying, right? You just turn on the lamp and all of a sudden you have sunglasses on, and that wouldn't be very good. And so when people are making these glasses, they probably pick AgCl because it requires just enough energy that the glasses become darker in convenient times, like when you walk outside in the bright sun, but not in inconvenient times when you're just maybe inside where you don't necessarily want sunglasses. And that's because of the difference in ionization energy between Cl minus and Br minus. All right, hopefully this was a good exposure to periodic trends. Remember that this is all based off Coulomb's law. If you're trying to explain any of these trends, you can always come back and look at what are the forces here in Coulomb's law that are in play.